Let's consider osmolarity, tonicity, and diffusion. We have got the inside of the cell, ICF, and the outside of the cell, ECF. ECF can be divided into interstitial fluid and plasma fluid. Plasma is just the liquid in the blood. Interstitial is the liquid between cells. Let's say this is a cell and this one, so the liquid between cells. So the interstitial fluid can also be transcellular. That is simply the fluid that is found within body cavities, which fills up spaces like as we can talk about the fluid that is just within the central nervous system, or let me just say the nervous system. We're going to call it CSF, cerebral spinal fluid, that is in the spinal cord. We can also have the synovial fluid, which is within the synovial joint. We can also have the fluid that is within the eye. So all those are transcellular fluids, which are part of the interstitial, which is extracellular. Inside the cell, we mostly have P's as the ions. What I mean is proteins, which are negative, phosphates, potassium. Also, magnesium is a major ion, one of the major ions inside the cell. While outside the cell, we have got chloride ions, sodium ions, bicarbonate ions. So those are the major ions. So these ions are able to move between these cells. We call them, of course, we know the movement of water from one compartment to the other down the concentration gradient is osmosis. So these ions are able to move, attracting water with them. We call them osmotically active substances. We have got other substances which are too small and they will just be moving anyhow without any limitation. And so those substances, an example I can give is urea. Those are not osmotically active. So the concentration of osmotically active particles is what we call as osmo. What is osmo is simply the concentration of those particles which are osmotically active. One osmo is simply equal to 1 gram molecular weight of a substance divided by the number of freely moving particles that each molecule liberates in solution. And so I can simply express that as osmo is molarity times N. This N is simply talking about the freely moving particles that each molecule is able to liberate in solution. If we talk about gram molecular weight, what we are simply talking about is the moles I can talk about, or simply the weight of a substance. So for biological solutions, the milliosmol is more commonly used. Now, what is osmolarity? Of course, just here, when we measure osmoles, the number of osmoles, that is the concentration, right? That is the concentration in osmoles. Now, we are going to mostly express it either in osmolarity or osmolarity. So this is just dividing by the liters of solution or the kgs of solution. When we have got R osmolarity, that is the osmoles per liter. If it is osmolarity, it is osmoles per kg of the same solvent that you are dissolving in, and this is mostly water. So for plasma, it will be mostly in osmo per liter. Now, because mostly for biological solution we express it in milliosmoles, the concentration is expressed in milliosmoles, then also osmolarity is going to be expressed in milliosmol per liter. So that is for biological solutions mostly. So the osmolar, if we have got L at the end, this means it's coming from osmolarity instead of osmolarity. So the osmolar concentration of a substance in a fluid is measured by the degree to which it depresses the freezing point, with one more of an ideal solution depressing the freezing point by 1.86 degrees Celsius. So what we mean by freezing point, this is just a point at which something gets to freeze. So the number of milliosmoles per liter of a solution equals the freezing point depression divided by 0.00186. So meaning if I want to calculate the osmolarity, not osmolarity but osmolarity in milliosmoles per liter, I'll just get the freezing point depression and then divide by 0.00186. Freezing point depression is simply how much freezing point decreases when you get to add something to this kind of solution. Let's say when we have got water, the freezing point of water is 0 degrees Celsius. But if I get to add salt to water, it will no longer freeze at 0 degrees Celsius. It might freeze at a negative temperature, and so it has dropped in freezing point. That is what we call freezing point depression. And so freezing point depression is negative because it is a drop in temperature. We are also able to calculate the osmolarity of a solution using this formula: 2 multiplied by the concentration of sodium plus glucose divided by the concentration of, by divided by 18, and then plus blood urea nitrogen divided by 2.8. So these are the major contributors of osmolarity. So meaning if I increase this concentration of sodium in solution, I'm going to increase the osmolarity. If I increase the concentration of glucose, I also increase the concentration. If I increase blood urea nitrogen, I'm also going to increase the osmolarity. Now let's take note of the units. They are all in per deciliter or per liter, meaning that we already have down, we have got what? Volume. Milligram per deciliter, milligram per deciliter, milli equivalent per liter, milliosmo per liter. That will be now the osmolarity. Milliosmo per liter. So if they've not given us the concentration of these in milliosmoles per liter, then what formula are we going to be able to use to find the osmolarity? To find the osmolarity, then we are going to use this formula. We'll get the concentration, we'll multiply by n, that is how many particles that substance is going to produce when it disassociates, and then we are going to divide by the concentration. Right. For now, we also have tonicity. Tonicity is simply the ability of the combined effect of solutes to generate an osmotic driving force that causes water movement. It might be not clear, right? So when we are talking about tonicity, it is different from osmolarity in that when I'm talking about tonicity, if we can look at this diagram. So the reference point here is the cell membrane. You talk about the concentration this side, you talk about the net concentration this side, the net concentration this side. If there is any difference, that difference is going to produce a net driving force to push particles in one direction. That is what we call tonicity. So if this is outside the cell, this is inside the cell, we have got different concentrations. Particles are able to move in that way. So let's say the concentration in, we've been told this is the cytoplasm, which is inside the cell, and then this is the extracellular, which is outside the cell. Of course, we can also tell because we can see chloride ions which are mostly outside the cell. So if the concentration in the cytoplasm, let's say it is 20, and then inside it is 5, meaning that that is going to generate a net combined force to push ions forward. And so ions are going to be able to move from the cytoplasm into the ICF because, I mean, into the ECF because ECF has got a smaller concentration. And so what is going to be happening? The cytoplasm is going to be losing ions. And when ions are moving, also water gets to move along. What happens then is that this cell will be shrinking like that. It will be becoming smaller. But if it is the other way around, if we have got a bigger concentration in ECF, ions are going to be moving in this direction, also pulling water with them. And so the cell is going to be becoming bigger and bigger. So that is what we call tonicity. So tonicity is going to describe the osmolarity of solution relative to plasma. Now, even if urea contributes to osmolarity, remember osmolarity is simply how many particles are in solution divided by the liters or the kg of solution. Now, when you're talking about tonicity, you're talking about those ions which are able to contribute for movement via uh, osmosis. So urea itself, it just gets to move between ICF and ECF like that. So there is no time when you are going to find it only in one portion. it is ever moving between ECF and ICF. So it doesn't get to give a force. It is not part of those ions which give a force, or those substances which give a force, a combined effect for solutes to generate an osmotic driving force. Because it is ever moving like that. It is not part of those which are going to be responsible for pushing ions from one compartment to the other. So it is contributing to osmolarity but not contributing to tonicity. So if the concentration outside the cell and inside of the cell is equal, then we are going to say solution is isotonic. Now if we have got a hypertonic solution, this means that in reference to the plasma membrane, the concentration is higher. If it is hypotonic, in reference to the plasma membrane, the concentration is lower. So remember, we're always talking about with reference to the plasma membrane. And so that is going to cause the movement of substances. All right. So these are some of the concentrations of substances within and outside the cell. Sodium is the major contributor of concentration outside the cell, 142 milliequivalent per liter. Also potassium. Sorry, not potassium, but also chloride ions and bicarbonate ions. These are the major contributors. When we go inside the cell, the major contributors to the concentration inside the cell, the first is potassium. We also have magnesium. We also have proteins. So just the P's: protein, phosphate, potassium, including magnesium. Of course, amino acids make up protein, so also the amino acids. Glucose is more in outside the cell than inside the cell. Right. So now, because of differences in concentrations, there is going to be diffusion of particles. So there is a net flux. When we talk of flux, it's simply the movement of particles from one compartment to the other. So there is a net flux of solute particles from areas of high concentration to areas of low concentration that we know. So the time required for equilibrium by diffusion is proportional to the square of the diffusion distance. So let's say a particle is moving from point A to point B, and the distance there is, let's say, 2, whatsoever the unit. From this statement, we can find that the time of diffusion is going to be square of the diffusion distance, meaning that if it is 2, the distance, square that, then the time it will take is 4, whatsoever the unit. So the magnitude of the diffusing tendency from one region to another is directly proportional to the cross-sectional area across which diffusion is taking place and the concentration gradient or chemical gradient, which is the difference in concentration of the diffusion substance divided by the thickness of the boundary. So if I'm talking about, we can simply simplify that by this equation, which is the Fick's law of diffusion. The rate of diffusion is simply equal to the area, what area? We are talking about the area across, or the area which it is going to be passing. That is basically the area of the plasma membrane, because that we are talking about which it is going to be crossing. So particles are going to be crossing the plasma membrane. So the thickness of this plasma membrane is going to contribute to the diffusion. So the magnitude of the diffusing tendency from one region to another is directly proportional to the cross-sectional area. So meaning that if I increase the cross-sectional area, particles are going to be able to diffuse much faster according to this statement. Okay, and it is also proportional to the concentration gradient, which is delta C that we're able to see on top there. And also we can see delta X, which is, so when we get to divide uh, delta C, which is a change, it is already explained here, the difference in concentration, and then divided by the thickness, meaning that if something is very much thicker, the rate of diffusion is going to be slower from this equation. If the concentration difference is higher, let's say where substances are going, the concentration is 2, where it is coming from, the concentration is 50. The concentration difference is higher, so meaning that the diffusion rate is going to be higher. But if the cross-sectional area is higher, the rate of diffusion is going to be higher. So we need to take note of, according to the Fick's law of diffusion, what is going to cause the rate of diffusion to decrease. So what causes the rate of diffusion to decrease is just the thickness, the area, and the concentration. Those are going to increase the diffusion rate. Right. So we also have what is known as the Donnan effect. When an ion on one side of a membrane cannot diffuse through the membrane, the distribution of other ions to which the membrane is permeable is affected in a predictable way. So let's consider this one. So let's say proteins are not able to diffuse through the plasma membrane. Why? Because proteins are big. What will be the effect of that? Because proteins are negative and they are inside the cell, they are going to be repelling negative chloride ions. So the negative chloride ions are going to be pushed outside the cell. That is why we find the chloride ions are more outside the cell. The chloride ions, because they're negative, they're going to be attracting positive sodium ions. So that's why we are going to find positive sodium ions more outside the cell. Because proteins are negative, they're going to be attracting positive potassium ions inside the cell. So that is what we are going to be able to see. And so we are going to be able to see this equation. The concentration of potassium plus the concentration of chloride ions plus the concentration of proteins. This is inside the cell. This is going to be greater than the concentration of potassium and chloride outside the cell. This is the Donnan effect. All right. So let's get to consider some practice questions on just what we have done. Solution A is 2 millimole per liter of urea. Solution B is 1 millimole per liter sodium chloride, and we've been given N, which is when this substance get to disassociate. Now when you are finding N, for example sodium chloride, when sodium chloride disassociates, it's going to form one sodium ion and also one chloride ion. So N is supposed to give us 2. Now, for us to be given that N is 1.85, it means that sodium chloride didn't fully disassociate. So N is simply representing how many ions are going to be there when the substance disassociates. Right. So how do we calculate now the concentration? Okay, the question is, are the two solutions isoosmotic? Isoosmotic means we just want to determine if they are having the same concentration. So let's first determine the concentration of the first one. How do you find that? The first thing, we need to determine the number of osmoles. Number of osmoles, remember, is given by molarity multiplied by N. And we know molarity is given in basically mole per liter. And then we are going to multiply that by N. So already this one is already in mole per liter. So meaning that we don't need to struggle with it. So then I'm just going to get that too. Of course, we said for biological substances, concentration is going to be most expressed in millimole instead of mole or milliosmole. So this is 2 millimole per liter. When we multiply by N, now for urea is a non-dissociating substance, meaning N is 1. So when you get to multiply molarity by N, what happens to the symbol, or the, let me say, the unit changes. So then the answer is going to be 2 milliosmole per liter. We have got a liter down, that is why I'm putting per liter. So this is the osmolarity. If we go to the other solution to also do calculate the osmolarity, then what are we going to get? Okay, so the osmolarity also is going to be molarity multiplied by n. So the molarity already will been given as 1 millimole per liter. Get to multiply that by n, which is 1.85. This is going to give us 1.85. The unit then, because we multiply by n, is going to be milliosmol per liter. So are these the same? No, they are not. Meaning that this solution is not iso-osmotic. Okay, so that is how we get to calculate this one. Now, what can we say about this since they are not iso-osmotic? Meaning this one is hyperosmotic in comparison to this one, and then this one is hypoosmotic. So that is a statement that we're able to use. Let's consider this one. Calculate the osmolarity of the following. We want to calculate the osmolarity of 1 mole of sodium chloride in 1 liter. So for the first one, let me first calculate the number of osmoles before I calculate the osmolarity. Okay, so the number of osmoles is given by number of moles times, we are simply going to multiply by how many ions this is going to form when it disassociates. So sodium chloride forms 2 ions when it disassociates, and we know this is 1 mole. So that will be 1 mole times 2. This will give us the number of osmoles, which is 2 osmoles. Now to calculate the concentration, which is in this case osmolarity. Osmolarity is going to be number of moles osmoles divided by the concentration. It's not osmolarity. So the number of osmoles, we have got 2 osmoles. The concentration is 1 liter. So 2 over 1 liter is just going to be 2 osmol per liter. So that is going to be it for this one. And then for the next one, B. Let's calculate the number of osmoles. Number of osmoles is going to be number of moles times the. Now, glucose, does it disassociate? It is a non-disassociating molecule. So meaning that how many molecules it forms when it disassociates is just 1. So the number of moles is 1 also times 1. So this is going to be 1 osmol. And then now we calculate the osmolarity. Osmolarity is going to be number of moles, that is 1 osmol, divide by the liters of solution. Now the liters have been given 0.5 liters. So this is going to give us 2 osmol per liter. Let's go to the next. 2 moles of calcium chloride and 6 moles of sodium chloride in 500 liters. How do you go about it? So let's first find the osmoles. The osmoles, we'll start with calcium chloride. We have got 2 as the number of moles times. When calcium chloride disassociates, it's going to form 1 calcium and 2 chloride ions. That means 3. Okay. And then plus, we have got 6 osmoles times. When this one disassociates, we're going to have 1 sodium and 1 chloride. That is going to be 2. So this is going to be 6 plus 12. This is going to be 18 osmoles. Those are the number of osmoles. And then we can calculate now the osmolarity, which is simply the number of osmoles divided by the volume. And the volume, that is 500 liters. 18 divided by 500. This is going to give us 0.036 osmol per liter. So that is it also for this one. Let's consider this one. Given the following concentration in plasma: sodium 142 milliequivalent per liter, glucose 90 milliequivalent per deciliter, and blood urea nitrogen as 15 milliequivalent per deciliter. We want to calculate the plasma osmolarity. How are we going to do it? So plasma osmolarity in this case is given by 2 multiplied by sodium concentration plus glucose divided by 18 plus blood urea nitrogen divided by 2.8. So this is going to be 2. The concentration of nitrogen is 142 milliequivalent per liter. Plus glucose, we've been given glucose as 90, divide that by 18. And then plus blood urea nitrogen as 15, divide that by 2.8. So let's see what we get. I'm going to start by 2 multiplied by 142 plus 90 divided by 18 plus 15 divided by 2.8. So this is giving me 294 as the nearest one number. Remember at the beginning we said the unit should be milliosmol per liter. So this is going to be it. Let's consider this one. Freezing point of normal human blood is negative 0.54 degrees Celsius, which corresponds to an osmolar plasma concentration. Remember, we gave the formula for this one. Let me just get reminders of the formula that we wrote here. The osmolar concentration in milliosmol per liter is given by freezing point depression divided by 0.00186. Okay, 0.00186. On top, we have got freezing point depression. So then this is going to be freezing point depression should definitely have a negative because it's a depression. But when I'm putting in this formula, I'm not going to put the negative. So divide that by 0.00186. Let's see what we get. 0.54 divided by 0.00186. And that is 290. Remember, for osmolar concentration, now even though this is osmolar concentration, now because we're talking about plasma, we are going to give it in milliosmol per liter. I think I had already mentioned that when we are writing somewhere. Okay, so it's mostly because this is plasma, we can even see there. Of course, plasma, we're going to give it in osmol per liter most of the times when you're talking about plasma. Now, basically, when you're talking about milliosmol per kg and milliosmol per liter, it is the same thing. Why is it the same thing? That is because the density of the solution in which you are dissolving, that is water, is 1 kg per liter. So whether you use a liter or a kg, it is basically the same answer. In this case for plasma. So then what will be the answer? Is it this one or this one? So we need to take also note of the unit. So it is 290 milliosmol per liter. The osmolarity of fluids. 1. ICF is hypertonic to plasma. Now we have got the intracellular fluid here, the extracellular fluid there. Of course, in the extracellular fluid, that is where we find plasma. So the osmolarity inside the cell and outside the cell should be equal. Otherwise, there's going to be diffusion and the cell might swell or the plasma might lose volume. So I wouldn't choose this one because it's saying hypertonic. Sodium exerts approximately 80% of plasma osmolarity. Actually, sodium is the one which makes up the highest concentration of plasma osmolarity, even up to 90%. So I'm going to take this one. Plasma proteins exert approximately 10% of the total blood volume. Well, I'm not sure about that one, so I'm going to leave it out. The osmolarity is affected by the volume of solutes and temperature. When you're talking about osmolarity, we've already used the one of the rules which gave us to say the rate of diffusion. Now this is, of course, let me not combine with rate of diffusion. This is osmolarity. That is just concentration. Concentration of osmolarity depends just on the number of osmoles divided by the liters of solution. So about the temperature, that is not part. Of course, it can depend on volume, but not the temperature. So basically, this is it. Now, plasma proteins are not really that high. They The major plasma proteins, of course, outside the cell we have got albumin, but it is not that high. Okay, it is not that high. The osmolarity of plasma is almost all due to plasma sodium. We know this is true just like from the previous one. It's almost all due to plasma because plasma sodium is the most abundant, contributing to the concentration about 80 to 90% like that, or even over. It's chiefly due to plasma albumin, not necessarily is the same as that of ICF. Osmolarity of plasma is the same as that of ICF. Well, from the previous question, if I remember, we said they are supposed to be the same, right? So that you prevent the movement of ions like that. So for this one is the same as that of ICF. I can tick this one. Increases significant in dehydration in vomiting. So let's see if we have got ECF here and then we have got ICF. When you get to vomit, you are going to lose fluid from ICF because what you are losing is not coming from the cells. So GI loss is lost from the ICF. So what you have lost is simply volume. The concentration of what you have lost is the same as that one in the cells. So the concentration doesn't decrease here when you vomit. What decreases is just the volume. So there is not going to be any increase in osmolarity. So this can't be true. Now, though we want to make sure that the concentration inside the cells is the same as that outside the cell, there's going to be a few of differences. Just like remember when we talked about this one effect, the Donnan effect. When you get to combine these concentrations inside the cell, what would we find is going to be greater than the concentration outside the cell. So even though we want to make sure that the concentration inside the cell and outside the cell is the same, there's going to be a slight difference. So if this was multiple choice and I was to pick an answer, so you have now to debate between this one and this one. The plasma osmolarity is the same as that of ICF, is almost all due to plasma sodium. Well, all of them they are more correct, let me say, but one of them, of course, if it is just one answer choice, you have to only pick one. So the plasma osmolarity is yes, almost or due to, but not necessarily everything. It is approximately a very small, let's say 80 to 90% making up the plasma osmolarity. And the word is used here, nice, almost, meaning that it is not everything, meaning I can do qualify myself this answer. Now, plasma osmolarity, because they've said is the same, it might necessarily not be the same because there's going to be a little of difference. Okay, there's going to be a little difference even if we want to maintain the concentration is equal. So I would qualify option A in this case. So we can do a bit of research. We find out what we are going to see is the concentration inside and outside the cell. We want to achieve it to be around 290 or 300 milliosmol per liter. But just in outside the cell, we have got plasma, we have got also the interstitial. We are going to see that these a little they are going to be different in concentration, but of course generally supposed to be 300, but they'll differ a bit in concentration. That is why just saying same, we can remove that. According to Fick's law of diffusion, particles flux will decrease if there is an increase in. Now, as we saw from Fick's law of diffusion, we saw the equation was dA delta C divided by delta X, meaning that according to Fick's law, particles would decrease. Particles flux would decrease if, meaning that what can cause a decrease in the rate of diffusion. So, what can cause a decrease in the rate of diffusion? Remember, this is proportional to these terms which are on top here. Meaning that if I want to increase the rate of diffusion, I need to increase these quantities which are on top. But if I want to decrease the rate of diffusion, I need to decrease any one of these factors which are on top. So I need to have either, of course, temperature is not mentioned on Fick's law, diameter. Okay, so if I want to decrease this now, rate of diffusion is inversely proportional to the thickness, which is simply diameter, isn't it? So it is inversely proportional. Meaning, if I want to decrease this, I need to increase diameter because I want to decrease the rate. So the diameter of the particles must what? Increase. Area of the membrane should decrease if I want to decrease the rate. Even, okay, let's talk of this thickness of the membrane. The thickness of the membrane, that is simply area, isn't it? We can talk about that. So the thickness of the membrane, we know that the area of the membrane is proportional to the diffusion, the rate of diffusion. Okay, I also confused this one. Here we're talking about the particle. So actually the answer we should qualify is this one. Thickness of the membrane is the diameter of the membrane. So meaning if the membrane is that very thick, the rate of diffusion is going to slow. So this is the one, not the diameter of the particle. So this is where we need to be very careful when looking also at the options that we are considering. Which of the following solutions I has high osmolarity? 0.2 molar sodium chloride. Let me calculate the number of osmoles for this one. Number of osmoles is simply concentration, which is osmolarity, multiplied by how many particles it's going to have when it disassociates. So this is going to have two particles and this is going to give us 0.4. So the answer is going to be what? Osmoles, because I've multiplied, or milliosmoles. And then for this one, the osmolar concentration is going to be, concentration is 0.3. Glucose doesn't dissociate, so we're going to multiply by 1. This is going to be 0.3 milliosmol. And then for this one, we are going to have 0.1. Also, urea doesn't dissociate. We are going to have 0.1 milliosmol. I'm expressing in milliosmol because these are biological active substances. And then the osmoles for this one, we're going to say 0.4 multiplied by magnesium chloride disassociating. We're going to have 1 magnesium, 2 chlorides, that is 3. So that is 0.4 multiplied by 3, and that is going to be 1.2 milliosmol. So because we want osmolarity, of course, we know it should be in milliosmol per liter. So we are not given the liter, so we should consider this as in the same, let's say in the same volume, meaning all divided by 1 liter. So the highest is this one. All right. The osmolarity of a solution is measured in. Osmolarity of a solution is measured in. Is it in molarity, millimolarity, osmoles, or milliosmoles? All right, so it is in milliosmoles because we are talking about physiology. You express them in milliosmoles. A solution contains 0.2 moles sodium chloride in 500 milliliters of solution. What is the osmolarity in milliosmol per liter? So how do you calculate the osmolarity? Osmolarity, first we are going to start with the number of moles, which is 0.2, multiplied by how many particles we are going to get. If sodium chloride disassociates, we are going to get 2. So the answer we find is going to be in milliosmoles. And then want to be in milliosmol per liter. So divide now by the liters of solution, that is 500. Now remember that this is in 500 milliliters. Okay, like that. Let's see what we're going to get first. 0.2 times 2, that is 0.4. And then we divide that by 500. That is going to give us 0.0008 milliosmol per milliliter. But we want it to be in liters. So I was supposed to convert this milliliter to liters. So we have got a milliliter here. I'm going to put a milliliter down and then a liter on top. In 1 liter, I've got 1,000 milliliters. So this will cancel with this. So meaning the answer that we find Okay, what I could have just done is 0.4 divided by these two zeros can cancel these two zeros. So 5 over 10 is 0.5. And this is going to give us 0.8 milliosmol per liter. So that is D. Which of the following statements about tonicity is true? Tonicity refers to the total solute concentration of a solution. Is this true? Okay, let me put a dot to see what we are going to think about. Try to think about it if it is true. Hypertonic solution can cause cells to shrink. Is that true? Let's look at this. We have got ECF, we have got ICF. When you're talking about an hypertonic solution, of course, the reference point is the ECF, meaning that the concentration is higher here than here, which is low. So what will happen is the substances will start moving like this. So what is happening to the cell? Sorry, not in this direction that I've put. Okay, so I was supposed to, okay, hypertonic solutions. Now, hypertonic solutions, of course, you are talking about reference to the cell itself. ECF is going to be hypertonic, and then ICF is going to be hypertonic, because we're talking about hypertonic solutions, meaning that the concentration is higher than the concentration in the cell. So this is concentration, not water potential. So because the concentration here is high, we want to dilute that concentration. What is going to happen? Water is going to be moving from the cell going in this direction. So the cell is going to be shrinking. This is true. If it is hypotonic, meaning that the concentration here is low than the concentration here being high, what is going to happen? Because the concentration here is high, you want to dilute that concentration. So there will be movement in this direction. So this cell is going to swell. Now, this is concentration. It is not water potential. If I'm talking about water potential, let's say ECF is here and then ICF is here. If I've got a high water potential here and then a low water potential here, high water potential, water is going to be moving out. Okay. So high water potential means the solution is hypotonic. Why? Because you have got too much water in comparison to solutes, and so water is going to be coming out. So this is a hypotonic solution, but it has got a lot of water. It has got lead to solute. All right. So even this option is correct. Tonicity refers to the total solute concentration of a solution. And I can say which are osmotically active, not just any other like urea. They should be osmotically active. So all the above are correct. The movement of water between the intracellular and extracellular compartment is primarily regulated by osmosis, active transport, diffusion, filtration. What regulates the movement of water between the extracellular and the intracellular? Primarily, it is osmosis, isn't it? So osmosis is the movement of water. Which of the following is a major cation in the intracellular fluid? Now we know that in ICF we should talk about what has got AP: proteins, phosphates, potassium. So potassium is a major cation. It's positively charged. So this is going to be the last question in this practice. Hope this has been helpful. Please, if it has been, remember to get to subscribe and also get to invite others for these tutorials. Thank you so much.